So recently I went to Niagara Falls and it was an amazing experience. There was water flowing around everywhere, birds flying around, and it was overall really cool. But when I decided to snap a picture, I saw something really unexpected. A rainbow. So how are these formed?
Well, every year around the top 400 physics students in America have to solve 6 problems, each explaining different phenomena in physics. This specific problem comes from the 2022 USFO, and it provides an explanation for the formation of rainbows.
In geometric optics, a caustic is a bright curve of light that appears when many incoming light rays are focused in the same outgoing direction. The most famous example of a caustic is a rainbow, which occurs when light interacts with spherical water droplets. Consider a spherical liquid droplet of radius r with an index of refraction between 1 and 2, suspended in air with an index of refraction 1. Okay, first of all, what the heck is an index of refraction? We haven't even finished reading the problem yet, and we've already encountered something we don't know. Okay, just bear with me for a couple seconds here while we finish reading the problem. Consider a light ray that enters the droplet with the distance b from the center, also called the impact parameter, then reflects once off the inside surface of the droplet, and finally exits. Our job is to find the total angle this light ray is deflected by, for part A. In order to do this, we have to find the deflection in the first refraction, then at the reflection, and then at the second refraction when it exits. To get the total angle, we can just add all 3 deflections. The reason we need to calculate this large angle is to figure out when a caustic will occur. Then, we can figure out how light will scatter in order to make a rainbow. We've encountered a lot of things we don't know, but in order to explain them, we have to first examine why light even undergoes this path. The speed of light was first accurately measured in the 1850s by a French physicist named Fizeau. First, he went up on a mountain and shot a beam of light through a wheel that he designed, which was rotating at a constant speed. The light then traveled until it hit a mirror on another mountain a few kilometers away, which reflected it back. Then, he adjusted the wheel's speed until he saw no light get through, so that the light that went through the gap between 2 spokes would get completely blocked by the next one. By doing simple algebra, he got an approximate value for the speed of light, 3 times 10 to the 8 meters per second. Around this time, it was also discovered that light was a wave, just like sound or ocean waves. It could reflect off surfaces, diffuse into a room, and diffract in different mediums, which are all wave-like properties. But where do these properties stem from? Well, it all comes from 2 things: constructive and destructive interference. Constructive interference occurs when 2 light waves are in phase, so their crests and their troughs line up with each other, and so they add up nicely. While destructive interference occurs when 2 waves are out of phase, so the crests and troughs don't line up completely. But what is phase? Well, phase is a number between 0 and 2 pi radians, or 0 and 360 degrees, and it describes how far into a cycle a wave is on. 0 phase is at the start of the wave, while 2 pi is after 1 full wavelength. Because 1 full wavelength corresponds to 2 pi of phase, we can set up ratios between the distance a wave travels and the amount of phase that it accumulates over that distance. Thus, by rearranging the equation, we can figure out that the phase is equal to the distance traveled by the wave times 2 pi divided by the wavelength. We call 2 pi over the wavelength the angular wave number and represent it with this little Greek k. Now, we can use differences in distances and times to figure out when waves will constructively and destructively interfere with each other. First, let's examine reflection. Suppose you have a source and receiver separated from each other, each with different coordinates. You might think that the only path light takes is where it just bounces off the mirror, like a particle with equal angles of incidence and reflection. But that actually isn't true. It can actually reflect off the wall in any way, at any angle, because at the point of reflection, the wave itself generates a spherical wavefront. that propagates through all angles. This is called the hue and Fresnel principle. This principle states that at every point on a wave, it generates new spherical wavefronts. This is seen in something like slits, where waves of parallel light can make a spherical wave. But even though it generates a spherical wave, it can still interfere with itself. And the only light we see is the light that constructively interferes with itself. Now we know why we can only see some paths of light, but not others. And we know how to find them too. If we can find a path that constructively interferes with nearby paths, it will be the one we see. Let us look at a path which reflects off the mirror with angles of incidence and reflection, alpha and beta respectively. Now, let us look at a small deviation, dx, away from this path, and calculate what the difference in phases between these two paths. Well, the difference in phase is just equal to the difference in distance times the angular wave number, which as mentioned before is equal to 2 pi divided by the wavelength. First, let's observe that the second path travels a bit of extra distance compared to the first one. So how do we find this? Well, we can approximate this extra distance as the edge of a right triangle. This is because as dx approaches 0, the two paths approach each other, which makes the legs of the right triangle approach the distance lost. Using trigonometry, we can see that this extra distance covered is just equal to dx times sine of alpha. We can also see that after the reflection, the first path covers a bit of extra distance. Using the same right triangle logic we used before, we can see that this distance is equal to one of the legs of the right triangle. And using trigonometry, we can calculate it to be dx sine beta. Now, the first path travels less distance dx sine alpha, but greater distance dx sine beta. So the phase difference between these two paths is just k times dx sine alpha minus dx sine beta. Now, for these paths to constructively interfere, this phase difference must be 0, which means that sine alpha must equal sine beta, or that alpha equals beta. That means the only path we can see when light reflects off a mirror is one where the angles of incidence and reflection are equal. Otherwise, it would destructively interfere with itself. What we've done is effectively minimize the times the light takes between the source and receiver. This is because paths around a minimum have no phase lag when compared to it. This principle is called Fermat's principle of least time, and it states that light will always travel in a way such that it minimizes the time it takes on that path. Now, let's move on to refraction. When light enters a new medium, it actually slows down by some amount. The amount it slows down by is called the refraction index of the material. For example, if a material has a refraction index of 2, it will make light 2 times slower inside it. Now, to find the path light takes when entering new media, we can use the same technique we used with reflection, but use it for refraction instead. We can also use Fermat's principle and compare the times. This time, however, I want you to try it. Consider a path with angle of incidence alpha and angle of refraction beta. The starting medium has a refraction index of n1, and the ending medium has an index of n2. Now, make a small deviation and compare the time of travel for each path. Once you've set this difference in time to 0, you've found the minimum. This time it should be noted that instead of comparing the distances between each path, you're comparing the time it takes for light to travel. So you have to account for the different velocities in the different mediums, which is where the refraction indices come into play. If you've accounted for the velocity changes correctly, you would end up with the equation n1 sine alpha is equal to n2 sine beta minimizes the time it takes between the source and receiver. This is called Snell's law, and it describes how light's angle changes through different mediums. Now, after all that, we can finally just solve part A of this problem. Well, let's solve it.
Remember, we want to figure out what the total deflection is, and to do that, we have to figure out what the first deflection is, the second deflection is, and the third deflection is, and then add them all up.
For the first deflection, we can use Snell's law. But to do that, we have to first find the angle of incidence, which we can do by extending this line over here, because then these angles are corresponding angles. And if we label this angle alpha, then we see that this angle is also alpha. But isn't sine of alpha just equal to the opposite over the hypotenuse, or just b over r? If we call the angle of refraction beta, then we know by Snell's law that sine of alpha is equal to n times sine of beta, because the index of refraction of air is just 1. But then, the deflection in the first part is just beta minus alpha, which we can rewrite to be arcsine of b over r minus arcsine of b over r divided by n. I rewrote this so that x is just equal to b over r. Then, for the second deflection, we know that these two angles, the angle of incidence and the angle of refraction, have to be equal, so they're both just beta. That means the angle of deflection is pi minus 2 beta. For the last refraction, we can use Snell's law again. However, we could also realize it's pretty much identical to the first situation, since an angle of beta comes in and an angle of alpha goes out. Thus, the deflection in the third part is the same as the first part, arcsine of x minus arcsine of x divided by n. Combining all three deflections, we can figure out what the total deflection is, which is pi plus 2 arcsine of x minus 4 arcsine of x over n. And that is our solution to part A. So that's it for this video. I don't want to drag this out too long. In the next video, we're going to be talking about how the intensity of light determines how caustics are formed. In addition, we'll also be finishing up the other parts of the problem in the next video. I hope this video made you appreciate how much work that a typical physics Olympiad student does in order to prepare for even doing this sort of problem. And as always, thank you for watching.